Welcome to today's video. Today I will be discussing the implementation of the Hack CPU. Let's get started. So, the Hack CPU chip is comprised of 3 input pins and 4 output pins, each serving a specific purpose in the CPU's operations. Let's have a closer look at them. First, let's talk about the input pins. Instruction is the first input pin. It has 16 bits. This pin carries the instruction fetched from the instruction memory. It then specifies the operation to be performed by the CPU, such as arithmetic, logical, or control instructions. In-M is also 16 bits. This pin represents the value stored in the currently selected data memory register. It serves as an operand for certain instructions and provides data for computation or storage. The reset. So this pin determines whether the CPU should be reset to its initial state, and when the reset signal is asserted, the CPU restarts its operations from the beginning by usually setting it back to 0. The program counter back to 0. So let's talk about the outputs. So there's 4 outputs: write M, address M, and PC. This signal is connected to the data memory and indicates whether the CPU wants to write the content to the data memory, and it enables the writing part. So the address M. So this signal represents to the memory address where the CPU wants to write the content, and it specifies the location in the data memory where the data should be stored. So out M, this signal holds the value that the CPU wants to write to the data memory. It also represents the data to be stored inside of the memory location, specifically specified by the address in the M signal. The program counter, the PC, so this signal holds the address of the future instruction to be fetched, decoded, and done by the CPU in the future cycle. It also keeps track of the program and determines the order that the instructions should be executed in. So that's it for the input and output pins. So now let's have a look at the Hack CPU from the outside. So the CPU contains many different types of logic gates that perform specific instructions. So let's go over it. So let's start with the ALU, which is the Arithmetic Logic Unit. So the ALU is responsible for performing arithmetic and logical operations. It takes inputs from the A register and also the D register and creates an output. Okay, so now let's talk about the A register. So the A register is a storage unit that holds data value. It can receive inputs from the instruction input or the ALU output. The D register. So the D register is similar to the A register, that it holds a value. And it receives input from the ALU output. The PC, which is the program counter. The PC is a register, and it stores the address of the next instruction to be fetched, decoded, and executed by the CPU in the next cycle. So we have 2 multiplexers. So the multiplexer selects one of the 2 inputs and forwards it as the output based on the control signal that it receives. So in this diagram, it is used to select either the value of the A register and the value of the data memory register, the M. So the instruction memory stores the instructions that the CPU fetches and executes. The instruction input comes from the instruction memory. Okay, now we have the data memory. So what the data memory does is that it stores the data that the CPU runs on and the M input represents the value of the current data memory register that it selected. So finally, we have something called control signals. So these signals control the operations of the CPU. It does things like determining whether the instruction is an A or a C, and specifies the function of the ALU, and it controls the program counter. So now what I'm going to do for you guys is I'm going to explain the HCL code. So it starts off with writing chip and CPU, and then it writes the inputs and the outputs. So the inputs are in-M, instruction and reset, and out. The outputs are out-M, write-M, address M, and PC. Now let's move on to the parts. So the first bit, it decides whether it's an A instruction. So if it's an A instruction, it sets the first bit to 1, and the next bit determines whether the instruction is a C instruction, which is the opposite of an A instruction. The next bit is used to check if the C instruction, CINS, and if the 5-bit instruction 5-bit is 1. This combination decides whether the output of the ALU should be stored in either the A register, or in the A register, which is ALU to A. It uses an AND and a MUX16. So the MUX16 stores the value into the A register. The next bit, so it decides if value should be loaded into the A register based on whether it's an A instruction or an ALU output. So starting with OR gate, which transfers an A instruction or ALU to A register, and the A register is used to store the value. So we have an OR and an A register here. Okay, and then the next bit selects A or M depending on the 12-bit, which is the instruction 12 value. It uses a MUX16. The next bit decides if the ALU output is loaded into the D register. It uses an AND and a D register. The D register loads the value of the D register from the ALU chip. Okay, so then the next bit is the code, which the ALU receives. It receives an A register output, a D register output, and the comp bits to show what function to perform on the inputs. So it sends the ZR and NG bits to PC, and then it sends an A register value to memory to select registers to read/write, and then it sends the ALU output to memory. Okay, now we're up to the final bit of the code. So this bit output writes bit to M register, which is the memory, if the instruction is C and D3 is set. So then the counter/jump conditions. So the first bit checks if condition jump if equal is satisfied, and then it checks if condition jump if less than is satisfied, and then it checks if either the ZR out and NG out is true when it's not 0. Then it negates the value of 0 or neg, which means it does the opposite of it. Then it checks if condition jump if greater than is satisfied, and then it checks if either jump if equal or jump if less than is true, non-zero, and then it checks if either JLE or JLT is true, which is also non-zero, and it checks if both the CINS and the jump to A are true, non-zero. And then what it does is it negates the PC load, which is the output from the AND. And then the PC will update the value of the program counter. And that's it for all the HCL code. Hope you enjoyed the video. Make sure to give me a good mark. Thank you.